In the last lecture, we have seen that in case of normal theta comma 1 population, there does not exist any UMP size alpha test for testing H colon theta equals to theta naught against HA colon theta not equals to theta naught. Actually, this problem arises in all the cases of distributions that belongs to the one parameter exponential family. In the present lecture, we are going to introduce the idea of unbiased tests. First, we shall discuss the generalized Neyman Pearson lemma, and then we shall introduce the idea of UMPU test, that is uniformly most powerful unbiased tests. Some examples, some results are discussed in case of one parameter exponential family. In modules 23 and 24, we have discussed the Neyman Pearson NP lemma for obtaining most powerful tests. In the present module, we shall consider a generalization of NP lemma. In this generalization, we considered the same optimization problem considered in the NP lemma, but increase the number of side conditions from one to many. As in the case of NP lemma, we first state and prove the generalized NP lemma, which is abbreviated as GNP lemma, for the non-randomized tests, and then we consider the case of randomized tests. In the non-randomized case, the proof of the GNP lemma is very similar to the proof of the NP lemma. Now we state the GNP lemma for non-randomized case. Let G0, G1 up to Gm be m plus 1 integrable real valued functions defined on the sample space script X. Suppose there exists at least one test function psi x such that integral over script x psi x into g jx dx equals to some cj j from 1 to m, where c1, c2, cm are some known numbers. Let psi naught be another test function satisfying 1 such that psi naught x equals to 1 if g naught x greater than summation over j from 1 to m kj into gjx equal to 0 if g naught x less than summation over j from 1 to m kj into gjx. This is right as 2, where k1, k2, km are some constants determined appropriately. Then we have integral over script x psi naught x into g naught x dx is greater than equals to integral over script x psi x into g naught x dx. We write this as equation 3. For all test psi x satisfying 1. In particular, when m equals to 1, we set g naught x equals to px comma theta 1, g1x equals to px comma theta naught, k1 equals to k, c1 equals to alpha. Then 1 is equivalent to the size condition, that is integral over script x psi x into px theta naught dx equals to alpha. Then the test function psi naught x in the above equation, and from 2 we see that psi naught x equals to 1 if px theta 1 greater than k px theta naught equals to 0 if px theta 1 less than k into px theta naught. From equation 3 we get integral over script x psi naught x px theta 1 dx greater than equals to integral over script x psi x px theta 1 dx, where psi naught x is an MP test, hence psi naught x is an MP test of size 1 minus alpha. Let us consider a proof of the GNP lemma. Let us define a function capital Qx This is equals to psi naught x minus psi x into g naught x minus summation over j from 1 to m kj into gjx. Then, as in the proof of Neyman Pearson lemma, it can be shown that qx greater than equals to 0 for all x belongs to script x. It follows that integral over script x qx greater than equals to 0. This implies that integral over script x psi naught into g naught x dx minus integral over script x psi x into g naught x dx is greater than equals to integral over script x psi naught x into summation over j from 1 to m kj gjx dx minus integral over script x psi x into summation over j from 1 to m kj gjx dx, which is equals to summation over j from 1 to m kj into integral over script x psi naught x gjx dx minus summation over j from 1 to m kj into integral over script x psi x gjx dx, which is equals to summation over j from 1 to m kj into cj minus summation over j from 1 to m kj into cj, and therefore is equals to 0, and therefore the proof follows. Now we state the generalized Neyman Pearson lemma for randomized case. Let g0 g1 up to gm be m plus 1 integrable real valued functions defined on script x. Suppose there exists at least one test function psi x such that integral over script x psi x into gjx dx is equals to cj for j equals to 1 to m. We write this as equation 4, where c1, c2, cm are some known numbers. Let psi naught x be another test function satisfying 4 such that psi naught x is of the following form: psi naught x equals to 1 if g naught x greater than summation over k from j from 1 to m kj gjx equals to some gamma x if g naught x equals to summation over j from 1 to m kj gjx equals to 0 if g naught x less than summation over j from 1 to m kj gjx. We write this as equation 5, where 0 less than equals to gamma x less than equals to 1 and k1, k2, km are some constants determined appropriately. Then we have integral over script x psi naught x into g naught x dx is greater than equals to integral over script x psi x into g naught x dx for all test psi x satisfying 4. Now we shall introduce the concept of unbiased test. A test psi is called unbiased test at level alpha for testing h colon theta belongs to script theta h versus ha colon theta belongs to script theta ha, which is a subset of script theta intersection script theta h complement. If expectation under theta of psi is less than equals to alpha for all theta belongs to script theta h and expectation of psi under theta is greater than equals to alpha for all theta belongs to script theta ha. We write this as equation 8. In module 32 we have already seen that UMP test does not exist for testing h colon theta equals to theta naught against ha colon theta not equals to theta naught, where the sample is taken from a normal theta 1 population. In such a situation, we may impose the restriction of unbiasedness and look for an UMP test in the class of all unbiased tests. Now we define the uniformly most powerful unbiased test which is abbreviated as UMPU. A test psi naught is called UMPU test at level alpha for testing H colon theta belongs to script theta H versus HA colon theta belongs to script theta HA if number 1 expectation of psi naught is less than equals to alpha for all theta belongs to script theta H. This is actually the size condition. Number 2 expectation of psi naught is greater than equals to alpha for all theta belongs to script theta HA. This is the unbiasedness condition. And number 3 expectation under theta psi naught is greater than equals to expectation under theta psi for all theta belongs to script theta HA. This is actually the power condition where psi is any test function satisfying 1 and 2. Note that if beta psi theta is equals to expectation of psi under theta, that is the power function of the test psi is a continuous function of theta, then 8 implies beta psi theta is equals to alpha for all theta belongs to script theta B. We write this as equation 9 where script B is the common boundary of script theta H and script theta HA, that is the set of points theta that are limit points of both script theta H and script theta HA. Tests satisfying 9 are called alpha similar on the boundary. We consider a very simple example. Let x1, x2, xn be a random sample of size n from normal theta, 1 population where theta is unknown. To test H colon theta less than equals to 0 versus HA colon theta greater than 0, consider the test psi x equals to 1 if root n into x bar greater than tau alpha equals to 0 if root n into x bar less than equal to tau alpha, where tau alpha is the upper 100 into alpha percent point of a normal 0-1 distribution. Here script theta H is the set of all theta such that theta less than equals to 0, and script theta HA, this is the set of all theta such that theta greater than 0, and therefore script theta B, which is the boundary of script theta H and script theta HA, is given by the set of all theta such that theta equals to 0. Note that on script theta B, root n into x bar follows normal 0-1, and therefore expectation of psi under theta is equals to probability under theta root n x bar greater than tau alpha, and it is equals to alpha for all theta belongs to script theta B. Hence psi is alpha similar on script theta B. Since it is more convenient to work with 9 than with 8, the following result plays a very important role in determination of UMPU tests. The proof of the result will be discussed later. Result 1. If the power function of a test psi is continuous, then unbiasedness of a level alpha test psi implies its alpha similarity. Now we consider tests for one parameter exponential family of distributions. We have already seen that in case of one parameter exponential family of distributions, one can get UMP test for number 1 H colon theta less than equal to theta naught against HA colon theta greater than theta naught by applying the Carlin-Rubin theorem. It was discussed in the module 32. It can be shown that, for example, one can see lemon, there exists a UMP test for the hypothesis H colon theta less than equal to theta 1 or theta greater than equal to theta 2 where theta 1 is less than theta 2 against HA colon theta 1 less than theta 2 by using the generalized Neyman Pearson lemma. If capital Tx is sufficient for theta, then the UMP test of size alpha for the testing problem 2 is given by psi naught x equals to 1 if k1 less than tx less than k2, equals to some gamma I if tx equals to ki, I equals to 1 comma 2, equals to 0 if tx less than k1 or tx greater than k2, where ki's and gamma i's are determined by expectation under theta 1 psi x is equals to expectation under theta 2 psi x is equals to alpha. But the problem is that there does not exist UMP test for the testing problem 3, which is h colon theta 1 less than equal to theta less than equal to theta 2 against ha colon theta less than theta 1 or theta greater than theta 2, and for the testing problem 4 h colon theta equals to theta naught against ha theta not equals to theta naught. For the testing problem 3 and 4 we can find UMPU tests by using generalized Neyman Pearson lemma. We shall now consider the testing problem 4. To find a UMPU test for the testing problem 4, let us define a set U alpha comma theta naught. This is the class of all tests psi such that E theta naught expectation of psi under theta naught less than equals to alpha and expectation of psi under theta is greater than equals to alpha for all theta not equals to theta naught. This is the class of all unbiased at level alpha for testing hypothesis under study. It can be shown that, for example, one can see the book of Lemon, the power function of E theta psi of any test psi x for the one parameter exponential family is continuous and differentiable. So the unbiasedness condition 8 implies expectation of psi under theta has minimum value at theta equals to theta naught, and hence we get expectation of psi under theta naught is equals to alpha. This is due to continuity, and expectation of psi under theta naught, its derivative actually E prime psi under theta naught is equals to 0, where E prime is this derivative of expectation of psi under theta equals to theta naught. This is so because here E theta psi has a minimum value at theta equal to theta naught. Now we define a class D alpha comma theta naught. This is the set of all psi such that expectation under theta naught psi equals to alpha and expectation of psi under theta naught, actually the derivative E prime psi under theta naught is equals to 0. Now we consider the following result. Under the assumption E theta psi is continuous, U alpha comma theta naught is a subclass of D alpha comma theta naught. We consider a proof of this result. Let psi belongs to U alpha comma theta naught. This is equivalent to E theta naught psi less than equals to alpha and E theta psi greater than equals to alpha for all theta not equals to theta naught, and therefore E theta naught psi equals to alpha, and E prime psi under theta naught is equals to 0, and hence psi belongs to D alpha comma theta naught. We consider another result, result 3. Suppose psi naught is the best test within D alpha comma theta naught, that is psi naught maximizes the power expectation of psi naught under theta 1 for all theta 1 not equals to theta naught, such that expectation of psi under theta naught is equals to alpha and E prime psi under theta naught is equals to 0. Then psi naught belongs to U alpha comma theta naught. We consider a proof of this result. Let us define a test function psi star x such that psi star is equals to alpha for all x. Then expectation of psi star under theta naught is equals to alpha, expectation of psi star under theta 1 is equals to alpha, and if prime psi star at theta naught is equals to 0. Therefore, psi star belongs to the set d alpha comma theta naught. Hence, expectation of psi naught under theta 1 is greater than equals to expectation of psi star under theta 1, since psi naught has the maximum power, and therefore expectation of psi naught under theta 1 is greater than equal to alpha for all theta 1 not equals to theta naught. Also, expectation of psi naught under theta naught is equals to alpha implies expectation of psi naught under theta 1 is greater than equals to expectation of psi naught under theta naught for all theta 1 not equals to theta naught, and hence psi naught belongs to the set u alpha comma theta naught, and it is UMPU at level alpha for testing h colon theta equals to theta naught against ha colon theta not equals to theta naught. From result 3, we see that in case of a one parameter exponential family, a UMPU test for the null hypothesis h colon theta equals to theta naught against ha theta not equals to theta naught can be obtained by determining a UMP test within the class d alpha comma theta naught. That will be discussed in our next module. In this lecture, we have seen that the simple Neyman Pearson lemma can be obtained easily from the generalized Neyman Pearson lemma. In this lecture, we have introduced the idea of uniformly most powerful unbiased tests. This test plays a very vital role in statistical inference. As we have noted that in case of one parameter exponential family, there exists UMP test for h colon theta equals to theta naught or theta less than equal to theta naught against ha colon theta greater than theta naught. Also for h colon theta less than theta 1 or theta greater than theta 2 against ha colon theta 1 less than theta 2. But in case of h colon theta equals to theta naught against ha colon theta not equals to theta naught, there does not exist any UMP test. And in this situation, we have discussed the determination of UMPU test.